Hi, everybody. I see the attendees are streaming in, flying into the room here, and we're really happy to have you here today with the IWRA webinar on sustainability of engineered rivers and arid lands. We have a really great panel, very experienced, very
Can you hear me?
Reputable panel
Yes,
of specialists
yes.
and experts. So we are really excited to have this. It's going to be
Okay.
I think one of the higher level webinars
Thank you,
so,
Stephanie.
we're looking forward to seeing you today, and we'll get started here in just 1 or 2 minutes. So you have an opportunity to go get a last glass of water or a last glass of coffee or whatever is appropriate for where you're at. Wow, we're a well-hydrated team here. This is great. So go ahead and get yourself ready, and we'll be starting in just 1 or 2 minutes.
Hi, Jurgen.
Hi.
Hello.
Hello, we can hear you
Yeah.
and see you.
Yeah.
Hello, Jurgen. This is Lars speaking. I can also see you. And we should, I don't know, how was it when we were talking? I think we should mute when others are talking, no? That is for the conference, no?
Mm-hmm.
Yes, that's polite, just like a conference call.
Yeah.
Should I start?
No, let's just.
I'll introduce you.
Yes. Now, I'm going to try to get Dr. North onto the panel.
I'm seeing you.
Oh, wonderful, Dr. North. We've had some technical difficulties getting Dr. North connected, yes. So this is the success.
I can see you.
Okay, everybody. We're going to get started. It's 4 minutes after the hour, and we have everybody here. So I'm going to welcome everybody to the International Water Resources Association webinar on sustainability of engineered rivers in arid lands, the challenge and response. So today we have a moderator of James E. Nickham, the editor-in-chief of Water International. And our panel includes Jurgen Schmandt, the professor emeritus of the University of Texas, Stephanie Glynn, Program Director, Hydrology and Watersheds at the Houston Advanced Research Center, Aysegül Kibaroglu, Chair of the Department of Political Science and International Relations at the MEF University, Dr. Gerald North, Professor Emeritus of Atmospheric Science at Texas A&M, and finally Lars Reed, professor at TH Culm. So, as most of you probably know, this is a webinar hosted by the International Water Resources Association. The IWRA is an international network of researchers and practitioners who work on a multidisciplinary range of water resource issues. We are a non-profit, non-governmental educational organization. The IWRA provides a global, knowledge-based forum for bridging disciplines and geographies by connecting professionals, students, individuals, corporations, and institutions, everyone who's concerned with the sustainable use of the world's water resources. We're really happy to have you here today, and we thank you for tuning in. As I said earlier, we have a really great panel of people who have been active in the field for many years. So, as you probably know, today our panel is going to talk about the ways that arid lands have been engineered to really be able to get the most out of the water resources we have there. You know, the engineering works on river systems, we're going to talk about several of them here today, have built up the reservoirs and have really increased the amount of storage that we can use for food production and for urban growing cities. However, of course, today with climate change ever present, the issues causing from climate change, in addition to reservoir sedimentation, depletion of groundwater, reduced environmental flows, everything's hurting the sustainability of these river systems that we've already been engineering. So we're going to look at these questions, we're going to address these concerns, and we're going to go into some really interesting case studies. This is some great research that's been put together, and I think you'll be very excited about this. So I'm just going to let you briefly explain the format of today's webinar. What we're going to do is have Jim, our expert moderator, I'll turn it over to him, and then we'll go through all the panelists, and then we'll save your questions for the end. We'll be hearing some short 10-minute presentations from each panel, And at the end, I will remind you that we're going to take the recording and we'll have the PowerPoints up on our website, www.iwra.com.org. We'll have that up there soon. So if you're interested in hearing more or sharing this with your colleagues or rewatching it as many times as you desire, we'll have it there for you. So with that in mind, I'd like to turn the floor over to Jim Nigham.
All right, yeah, thank you very much, Scott. I'd like first to kind of give an introduction to the webinar series because both Scott and I have been involved with it from the beginning. It originated as Scott's idea, as I recall, and as a way of publicizing initiatives that were published in our the official journal, Water International, of the International Water Resources Association. Those of you who are members are no doubt quite familiar with it because you get it for free. Since then, the webinar series has actually taken off and is now being used for all sorts of topics, including some very topical and cutting edge issues in water resources. We've recently had one on COVID and sewage, and another one on women and resilience. So I'm pleased. This is, in a sense, yet another new initiative for us. It's not based on a Water International special issue, although I will point out that there is an article that described this project in 2017 that appeared in Water International, and I believe that will be online for open access based on this this webinar series for those of you who somehow are not yet IWRA members. Okay, so let's get started with this because we have 5 presenters. We only have 90 minutes, and I think we're going to get an awful lot of questions on this one, good ones. Starting off, the paterfamilias of this activity, Jurgen Schmandt will introduce what SERIDAS is. It's been around, I understand, since it was a glimmering in 2013, so this has taken a long time to come to fruition, and now we have it. It's quite a significant project. Okay.
Please show my screen. Can you hear me?
Yes, we can hear you and we can see your screen. Looks good. Just go to the PowerPoint, your PowerPoint, like we.
I'm deeply impressed by the work of IWRA, and I thank you, Scott. I thank you, Jim. And now I will click on my introductory and I will hope that you can see it when it opens. Can you see it?
Yes,
Yes.
we see it.
Yes.
Okay.
Slideshow.
Yeah, just go to the slideshow as we practice. Yeah, just like we did yesterday.
SERIDAS stands for Sustainability of Environment of Engineered Rivers in Arid Regions.
Yeah.
How did we come to this word and this project? About 20 years ago, a small team of Mexican and US scholars looked at the water future in the border river between the 2 countries, the lower Rio Grande, also called Rio Bravo, in Mexico. We found that by 2030, not that far out, there would be 30% less river water compared to today. We'll tell you later about the reasons, but here's what puzzled us. Is the Rio Grande situation similar in other rivers around the world? If so, what are the prospects for these kinds of rivers with heavily engineered reservoirs? And most importantly, what is the river future going to be, considering the impact of climate change, the gradual loss of storage due to reservoir sedimentation, and population growth in the river basins? What we did on the Rio Grande was found in similar ways in a study by one of our members, Antonio Magalhães from Brazil. He will talk about his project in our second webinar. To answer the questions, we started 6 years ago the SERIDAS project. Here's a quick look at how all continents are represented: Colorado, Rio Grande, San Francisco, Limarí, small one in Spain, Lucar, the Euphrates Tigris, about which you will hear today, the Nile, about which you will hear today, the yellow on the program for December, and the Murray-Darling also on the program for December. All of these rivers are important for irrigation and food production. The irrigation level changes quite significantly. The San Francisco is the highest, but all of them control the regional economy and produce about 40% of the world food production. Why did we pick these rivers? They have 4 common features. The water comes from far away, snowpack or highland rains. For millions of years, the spring floods brought fertile soil which accumulated around the borders of the river, is the reason for the success with irrigated agriculture, even before it was irrigated artificially. This happens in the arid or downstream or semi-arid downstream region. And in order to continue with successful irrigation, we invented the irrigated system, relying on large, modernly engineered reservoirs. The first one, 1892, built by the Brits on the Nile, followed by 2 in the early 1916, 1912 on the Rio Grande. All of the rivers we selected, all of the engineered rivers in arid lands have followed suit, built one, several large reservoirs, create a new lake behind the reservoir, and are the source for a detailed distribution channel to irrigation districts and farmers. The rivers we have in the project are important in terms of what the reservoirs can do for flood control. I mentioned food production. They provide drinking water to growing populations. Some of them are also important for producing energy. We came with a stark warning at the beginning of the SERIDAS project. The system we have built over the last 100 years is suffering from climate change, reservoir sedimentation, overpumping of groundwater, and population growth. We will spend a good deal of our time today, and even more so in December, on what needs to be done to face those challenges. Let me say a word on the origin of the challenge and response sequence, which we use consistently in our work. It goes back to a British historian, Arnold Toynbee, for whom history developed as a sequence of challenges and responses. And the interesting side of the challenge response sequence for us is that the outcome of a challenge can be good, bad, medium. It depends on human intelligence, human determination to make it happen. The challenges we are most concerned about in our SERIDAS project are two. Less water, I mentioned already the main reasons, and reduced environmental flow. We will hear about this from Stephanie. We have a number of response strategies, none of which has been tested to the point of saying this and only this is the way. We will introduce to you an important concept. We call it the dependable yield. How much can the river deliver, does the river deliver under current conditions, even under extreme drought conditions? Once we know the number for the dependable yield, we have to take action and adjust our strategies. Okay, I have taken much of your time. Let me just show you who we are. You see your moderator in a green shirt. You see a few people whom I should have referenced. Here's one of the contributors to our first study in the Rio Grande. 16 people. I should close with mentioning how we select them. We select one person who is knowledgeable about one of our rivers, and we select a group of other people who are knowledgeable about the challenges like climate change. We'll hear about climate change in a moment. This interaction between river expert and problem expert was critical for the success of our project. Our project will be completed next year with a book, 19 chapters, which is in the process of being published by Cambridge University Press. It will be available online in March. The paper version will be out 1 year later. Let me conclude with a heartfelt thanks to my co-editor, Aysegül, who is on the program today, and two unbelievable performers, two graduate students of mine, Regina Bono and Sephra Thomas. Without them, the book would never have been finished. Thank you all. Scott, you have put together a wonderful session.
Okay, thank you, Jurgen. Next, hello. Next on the program, I believe we have Gerald North, who will talk about the one big issue, climate change and its prospects for rivers. Gerald, are you there?
I'm seeing you, but you're not seeing me. I can hear you, but I think you cannot hear me. Is it correct?
I can hear you
fine.
We
can
all
hear
hear.
Amazing. Okay. Now, what I have to do then is figure out how to get my PowerPoint on. And I think
I had sent you an email a few minutes ago, since we were able to connect earlier. And it should come up on your screen with a box that says to share your screen. Do you see that?
Is it down at the bottom?
No, it should pop up right on the front of your screen. It should be right there. Do you see it?
No.
Here, let me try one more. I'm gonna try it again. I'm gonna send it right now. It should pop up right now, right on the front of your screen. Do you see it there?
Well, I see a thing over on the left, but it still has my video off. I don't see you.
It should be right there on the front
I'd like
of.
to capture this computer screen. Yes, open the screen. Okay, screen is open, but where do I see share?
It should be right in front of you.
Well, the whole computer is right in front of me.
Okay, good. That's important. Okay, I'm gonna send it again. It just pop up right on the front of your screen. The panelists can.
Over on the left, a column of all kinds of stuff. I can't see share though.
It should just a box should pop up on your screen, and it should say, "Do you want to share your screen?" And you just have to merely click yes.
Got it.
I have it up if I can share my screen.
Okay, we can do that. Can we do that? We'll just share with
if you have my PowerPoint, you can put it on there.
Got your PowerPoint.
Yeah, that'll be fine. Only I'm not sure I can.
I think it's going to make that possible. Although
I did.
I don't know. I'll be sharing both my screens. Excuse the junk on the side if it's that way.
Okay.
Okay. So.
There you go. That looks good.
I see on my screen my first slide. Is that good?
Beautiful.
Good. Okay. Okay. I'm Gerald North, and I'm going to talk a little bit about climate change. And can everyone hear me? I don't think you can. Maybe you can. This is taken from a talk that most of the panelists attended in Bellagio, Italy in 2017. So next slide, please. Can you do that? What do I do? Next slide.
Okay.
You go.
Oh, okay.
I can't hear you now.
You want me to continue on this?
Okay, yes, I see freshwater availability. Yeah, okay, let's, I can see, I think what you see. Good, okay. And good, thank you. So it's hardly a surprise to this audience. It's not a surprise that the warming is going on. It's real, it's very serious. Fresh water availability may be the most serious consequence for societies around the world. Here is a picture, a graph of the global average temperature going back to 1880, and you can see if you touch the next thing, there will be an arrow on there. Hello? Yes?
Next one? Oh,
Next
that
step.
one. Okay.
There it is. That's right. Okay, so you can see there's a slope here of about 1 degree per century. And hit the next one, please. And you'll see, you don't, I see yours is a little bit older than what I have in my own, but that's fine. Most elementary and robust considerations suggest that the greenhouse effect is real, and now next, thank you, a brief reminder of the weakness of climate model simulations. I want to warn everyone how these things are fairly blunt instruments, but we do the best with what we can. So there's a big uncertainty in climate sensitivity and the lags. So in other words, the forcing, that is the change of CO2, but then the response of the Earth lags behind. And that's getting both the sensitivity and the lags is problematic. The lags come from the ocean, the long response time of the oceans. Precipitation is also hard to model compared with temperature change or the rise of sea level. Those are pretty easy. Temperature change, but precipitation is difficult because it depends on the model's ability to describe the circulation of the atmosphere and so forth. No, next one, please. Good. GCMs are using very fine grid resolutions. We're making great progress in that direction. That usually, when you make the grid finer, you get a more realistic simulation. But then there are many GCMs. We have a big diversity of them. So there's a spread in the results, which is good because that tells us that lots of different things are going on. Different modelers address things in different ways. One more, please. Number 4. Good. Climate feedbacks are the main concern, probably contributing maybe plus minus 50% errors in global scale sensitivity. So in other words, if we say at the end of the century, we're predicting 3 degrees, make that, let's say, between 2 and 4. Okay, something like that. So that's the kind of uncertainty that we have. But even more difficult is putting in exactly how much CO2 there is in the atmosphere. We don't know that. And aerosols, the tiny particles that are floating around. So these are also really on the board to worry about. So on the left, you see the change in temperature. This is the distribution of its change. And notice at the bottom, I say a funny but useful scale of the contours. What this means is the models all wind up with different amounts of change at the end of the century. So we give here the amount of change in the map per change. This way we can organize what all the models do, and you get a better, clear picture of the geographical distribution of the change. And you can see on the left, on the red shows that the continents are warming more rapidly than the oceans. That's a very robust finding. And also, certainly the North Polar area is warming much more rapidly, and we all know that too. And also a small warming in Antarctica. On the right, you see the precipitation change. It's done also with this percent change per degree of a model. So this helps you to, when you do that, they all look a little bit more alike when you divide that. So what you see, and we can skip on to the next slide because I have a blow up of the precipitation. So here you see that in the, let's see if I can't use my pointer, but I think we can describe it. What you see is that the subtropical areas, that's where it's yellow and tan. Those are areas that are going to be dry or have less precipitation. You can see that up at the North Pole, far more precipitation, much greater change in percentage. And also around the equator, of course, is the intercontinental, that's the ITCZ going around the equator. We expect it to get more rain. But you can see, though, that the subtropics, this yellow area between the equator and the storm paths, you can see there that they are going to be getting less precipitation. The little dotted areas are are places where it's statistically significant. If you look at the United States, for example, the American Southwest, pretty well good statistical significance there. In the East Coast side of what I call from the center of the United States to the east, a little bit more rain, but not enough to be statistically significant. And now go over into the Mediterranean. You can see there much less precipitation. And down in Australia, again. Now China and Siberia, probably more precipitation, at least according to these model results. Let's move to the next slide now. Actually, it'll just show us here some highlighted areas. Here is a precipitation. This is the 10-year average. Now this is the past, not the future. This is the climate average. And what you can see are the green areas are where there's more rain, and the white areas are areas where it's nearly desert-like or very arid. And what we think is going to happen is that these white areas are going to expand their area polewards in both hemispheres. So this seems to be also a pretty robust finding among the models. This is not models. These are data here. This is from the tropical rainfall measuring mission, which when I worked at NASA, I was one of the principal promoters of that scheme. Okay, so next one now, please. Good. So here is a schematic, a very crude picture of how the atmosphere works on its large scales. At least this is very schematic, but it's quite helpful, I think. What you see is where it says the Hadley cell on the left side. That's the one that's most important for what we're talking about now. So the Hadley cell might expect, we're finding that in data and in model studies that the Hadley cell is expanding polewards. In other words, its northern edge is moving probably up a little bit further than roughly the 30-degree latitude mark now. And those trade winds, which are along the surface, the red lines, those are steady streams of air flowing along the surface. The air is returned in the cell up in the upper part of the troposphere. And you can see in the westerlies above, those are the storm tracks that pass over the middle latitudes from west to east all around the world. So they provide lifting, the instabilities in the atmosphere provide lifting, and therefore if moisture is available, you get rain. So let's move on. Next one, please. You see sinking air. And so here again is a blow up of that same picture that just gives you a better idea compared with that idealized picture. And down here are data, so you can kind of see this correspondence. And so the problem is that in our simulations, or that in our study here, many of the rivers that we're looking at are going to have smaller amounts of precipitation, at least according to the models. So let's move on. Next one, please. Yeah, the Hadley cells expand. And I'm taking these next few slides from a couple of papers by an old friend of mine, Qian Fu, who is at the University of Washington. These are his colleagues, many of them students of his, but they come from different places. So if you, you can go and read these papers if you wish. They're now probably getting a little old, but I think what they found a few years ago is probably still prominent in our model findings. Go ahead, next one, please. This is just for you to use if you wish. Okay, so what they did was they considered an aridity index. And this is something that can be computed from the models. And that's the nice thing about it. And it's called the aridity index. And I'll show you what it looks like on the next slide. But it's the ratio of precipitation on the top. And this, could you back up one, please? Let me finish on that one. Yeah, no, back up. Hope you can do that. Yeah, good. So the potential evapotranspiration transpiration is the PET. Sorry, aging is sometimes gets into my way. Yeah, so it's defined as the amount of evaporation that could occur if a sufficient water source were available. Now, a lot of you who might be watching this webinar are hydrologists, and you may know far more about this than I do. But the P you can get from climate model simulations, and you can also get the PET. So it's a little bit hard to actually find the evaporation itself. That's kind of tough to get, but you can do this ratio. Okay, now let's move to the next slide. And so this shows the present day dry lands. So you can see that Western North America, the pointer was just looking at the Sahara. Clearly the Sahara is a hyper-arid area, and there are places out in Asia that also are like that. But the red areas are arid and the orange are semi-arid. So what we would like to know is when we go forward in time, will these areas expand and will they get worse? So you can see there that Australia is one of our problem areas, and we have one river in Chile, and it is a problem area as well. And and also the Tigris, Euphrates. So all of these are problematic. So we'd like to know how this changes. So next slide, please. That will show the change. And what you see are these little rim-like things that are around, and what they're indicating are the expansion of these dry areas. And you see them in many of the places where our rivers lie. And I did have a slide that I was going to show you if we had gotten my most recent one in. Jurgen suggested that I show again the rivers that he showed in his slide, but I think you can remember pretty much which ones they are. But that didn't get updated here, so sorry. Let's go to the next one. It blows up just the western part of the United States. So on the left you see now, and on the right what you see is intensification of the dryness, but also in that vertical line, it moves to the east. So this area is expanding. So that's what these simulations and then the analyses of the simulations by Fu and his colleagues have done. So let's carry on. Now, next slide, please. So see here, you see the arrows where it's moved. Let's skip this one. I took this one out just to keep, though I don't like I think they're ugly. So the next climate variability is driven by a lot of these oscillations that occur in the climate system. And one is called ENSO, that's the El Nino Southern Oscillation System, which is probably the biggest of these. And it flip-flops every few years let's say between 3 and 5 years. And then there's some others like one is called the North Atlantic oscillation, the Pacific decadal oscillation. So that one is very slow. It flips on decadal time scales, and they are strongly seasonal. So let's move on. Next thing. Many of these affect the rivers that we're considering. So for instance, in Texas, when we have a big drought, it really is often correlated with the phase of enso. In other words, it's when we have a La Nina that this part of the world is strongly affected by that, even though the origin of it is way out in the middle of the Pacific Ocean. So these others, the North Atlantic, tickles the weather patterns in Europe. So, and the PDO, that last one, really is quite long-lived decadal things. And these are rather schematic findings, although ENSO and the NAO have been studied pretty seriously for quite a few years. And we're beginning to know a lot about them, but we cannot really predict when they would come. We know something about the physics of how they work. It's a kind of, both of these are interactions between the ocean and the atmosphere at the interface. And oceans do have these periodic, quasi-periodic events. Okay, so many affect the rivers, sometimes more. This is fine just to show you. Here's the ENSO, and I have a few more slides that I would have taken out. Let's move on. Thank you. So that just shows you where the warm waters are. Here you see, well, this is fine. This just gives you an idea. When there is an ENSO, these regions are affected in December, February, now below June and August. And I actually was going to cut these out too, but you get a feeling for when these events happen. Look at this one, La Nina, and you can see in southeastern, all the way across the southern part of the United States is quite brown. But these are felt all over the world. They are global events. And, you know, one ENSO may be a little different from the previous one. They're not exactly periodic. So that's the way it goes. Anyway, they do affect our rivers. And what we don't know is, in our climate model simulations, they're really not quite good enough yet to tell us, will there be more ENSOs? In other words, will the frequency increase, or will they be stronger? And we don't really know the answer to that. So that's troubling. All right, let's move on. So those are just some events that we need to worry about. Here's one that is really quite odd. This is a Texas summer. So I'm giving you Texas because I live here, and I just happen to have this slide. And this is a graph showing when it's hotter in the summer in Texas, and on the ordinate and on the abscissa when it's wetter. And you can see that each one of these little diamond shapes is a year, one summer. And you can see that there is a correlation. When it's hotter, it's drier. But look what happens. There is this one outlier, 2011. It was an incredible drought here in Texas, and it was also coinciding with a La Nina. But you see, there are many ENSO events in that pattern, but only that one. The fact is, it was an ENSO and something else too, and they both reinforced each other to give us this weird drought. So we may very well find more of these kinds of extreme events in the future. All right, so let's move on. I think I'm really at summary now. Yes. Okay, so global warming increases the temperature and it changes the PET everywhere. So this can be computed in our models. Number 2, dry lands, expect area maybe 10% might globally increase. Global warming also causes expansion of the Hadley cells. We talked about that. Go ahead. With consequences for subtropics, middle latitudes, and of course our rivers, for the most part, run right across these areas. So are the eastward mid-latitude winds, that's another question that we didn't raise, but that is a small feature. Fine. Next one. Keep where we are. Natural variability of these things, we're still playing with that. Next one. I'm getting an echo. Monsoons are tricky. We don't really know for sure yet whether they will be stronger or not, or more erratic. So those are questions that are still open. Natural variability is very large in an individual basin. Probably overwhelms global warming signals. Sometimes funny things can happen with even 60 years or so intervals. The number of extreme dry events seems to be increasing. We already see that. And other things, that I've not even touched on are really happening today. Our western states of California and Oregon and Washington have just been in unbelievable fires. And they happen at other parts of the world, maybe at alternating years. We don't know. But so these are very subtle things that are happening, but they do seem to be on the rise. Okay, next, please. This may be near the end. Next slide. I think it is the end. Yes.
That was it.
I'm done. Thank you very much to everyone, especially Jurgen and Aysegül for so much hard work they've done. Good.
Okay, thank you, Gerald. That was, of course, a little more than 10 minutes, but quite comprehensive. Not reassuring for most of the river basins, I think. So now can we kind of move underground a little bit and go to Stephanie to talk about both groundwater and environmental flow.
All right, thank you very much, Jim. Let's see. And let me switch it because I think you guys are seeing, whoops.
Yeah, just like, yep, there we go.
Okay, do you see the big slide now?
Yep. Perfect.
All right. Well, thanks everyone. Thanks for joining us today. And you've heard from one kind of special section expert, Dr. North, and I'm afraid I'm going to follow probably with not such good news either. But I'm going to talk today about both inflows and groundwater, and I'm going to talk about them in 10 minutes. So you are going to get a very brief kind of overview of these, but we dive deeply into them in the book. So if you're interested at all, then I urge you to check out those. It's 2 separate chapters in the book, so it gets a lot more detailed. So today I'm just going to kind of talk to you about the importance of each one and then their context in the big picture of SERIDAS. So we're going to start with dams, because of course what we're talking about is engineered rivers and how dams impact inflows. And the 3 big takeaways are it's quantity, timing, and quality of the water. So dams impact all 3 of these things, and all 3 are important for downstream ecosystems. So when we're talking about quantity, of course, that's overall how much kind of gets downstream, because of course you're going to limit that with the dams. When we're talking about timing, and this goes back to a lot of what Dr. North was discussing too, it's when those inflows get there, and we'll talk a little bit about this on the next slide, but timing can be so important for certain habitats, for certain ecosystems, for certain species. And quality is important as well, of course, and I think the river experts will speak to this, but when you have those dams on there, you really are impacting the water quality, and specifically some of the water quality that gets downstream. So why are those altered flows so important? It's those flows that determine the physical habitat in a river. So you've got a lot of species downstream that really have evolved their life history strategies to that natural flow regime. So they are used to certain pulses. They are used to certain timing of those flows, as we discussed before. And when you alter those, some species can compensate for that and respond and even tweak their life history strategies just a little bit, but some can't. There's some fish species, for example, that really depend on those riffle flows to be able to lay their eggs. And if they don't get those specific timings, then they can't do that. And so all of our major rivers within SERIDAS actually show signs of some species being able to evolve and some species can't. And what you get then, and this is really important for a lot of our rivers, is increased stress on native species. And so you get a lot of invasive species that come in as a response to those altered flows. So this shows an image of all of our rivers. And what you're looking at here is modeled probable environmental flow. This is in million cubic meters. And so can you guys see my mouse when I move it or no?
Yeah, we can see it a little bit.
Okay, good. All right. So your legend is down here, and this shows that modeled environmental flow. So your dark blues and greens are kind of your highs. Our SERIDAS rivers here are outlined. And so what you see is that for many of our rivers here, you're seeing a lot of projected decreased environmental flows. And so what that means is you already have decreased environmental inflows because of the dams, and then due to climate change, many of our basins are projecting even more decreased environmental flows. So it just speaks to more stress on these river basins and the need for management for the future. And I just wanted to note, this is just flow required to maintain the current conditions. So as the figure shows, some river basins are currently at this time in peril of low flow. So again, just to stress that those future management scenarios really need to plan for strategies to increase these inflows. Okay, now we're going to speak a little bit about groundwater. I want to start with kind of the surface groundwater interactions because they really do rely on one another, and it's important in these river systems to really understand those quantitative linkages between groundwater and surface water, so that when you're planning your overall budget, and particularly again in the face of climate change, you can really speak to how much they relate to each other. And as we talked about earlier, we have low flows in these river basins from some of these dams. That can lead to less recharge, particularly if the surface groundwater interaction areas are impaired, and this can lead to overall less inflow. Let's look specifically at some of our basins. And again here, oops, I'm sorry, let's go back. Okay, again here, our SERIDAS basins are outlined, so you can see these on the screen. The dark green areas are areas with kind of very high groundwater resources and groundwater recharge. You can see that some of our river basins fall in that area. These little red dots show areas of natural groundwater discharge. So this is where you might have some of that high surface water groundwater interaction. And you also see here the areas of low rainfall. It kind of got cut off on my screen. I don't know if you can see it, but it's those blue dots. And so if you come up here and look, you can see that some of those are those areas. And again, those are some of the same areas that are going to be stressed from climate change. If you go back and look at some of Dr. North's slides compared to these, you're going to see that a lot of these global groundwater basin supplies that might have some of the very low supply are also the ones that are going to be stressed according to more arid environment from climate change, as well as areas that don't have a lot of high recharge. So I wanted to give an example from Texas just to talk about management and the fact that we need new ways of thinking about arid lands with these high evaporation rates. And that we have in the state of Texas, we have a water plan that kind of projects out how we are going to meet the water demand. And one thing that in some of the past plans, we had a lot of proposed reservoirs, which are the most expensive items in the plan. But Texas experienced a major drought in 2011, and the evaporation loss from Lakes Travis and Buchanan, which are major lakes that supply water for the city of Austin, was greater during that drought than all of the water used by the city of Austin. So again, just to speak to a lot of the loss of those high evaporation rates with arid lands, and again, with the stressor of climate change, we need better management strategies for a lot of these basins. So to kind of talk about a case study on environmental flows, we're going to look at the Rio Grande. We're also going to be looking at the Rio Grande for groundwater case study. And the flows below the Elephant Butte Dam, which is a major dam on the Rio Grande, they're low in volume, they're intermittent, and a lot of times in recent years, we actually don't have flow from the Rio Grande into the Gulf of Mexico because we have such low flows. And you can see the decline in flow there from 2.5 million acre feet to 1.1 million acre feet. So this goes back to what I was talking about, some of those impacts, reduction in flow and flow variability. Okay, so you've got darters, which are adapted to riffles and shallow runs, but not pools. Other species like bass need the deep pools. So when you have an engineered river, you've really kind of taken away those natural flows. And as well with climate change, we are looking here, here's a picture that shows it very well, these years where the Rio Grande just does not empty into the Gulf of Mexico as it used to. So then you're impacting the Gulf of Mexico too, because you are not getting a lot of those inflows that are so necessary for some of the lifelines of those marine species, like your shrimp, like your crabs, like your snappers. And then the groundwater case study for the Rio Grande, we have a lot of shared borders with the Rio Grande between nations, the United States and Mexico, and between states, Texas, New Mexico, and Colorado. And aquifers do not recognize these kind of political boundaries. So if one area is going to pump too much, it's going to impact other areas. There's ongoing litigation between these states right now over rights and usage. And the countries have to work together too to manage their aquifers. Right now, there's a kind of historic case ongoing in the states where Texas, which borders New Mexico, is claiming that New Mexico is violating a longstanding compact by increasing groundwater pumping. And that groundwater pumping is actually reducing inflows dramatically into the Rio Grande. So this goes back to that groundwater surface water linkage I was discussing earlier. So what does this mean for our SERIDAS rivers? We need to really think about sustainable groundwater and inflows. We have to look at some of these climate trends and projected trends in groundwater and surface water usage. Is it going to threaten water quality? Will we be able to sustain current groundwater supplies? What are we looking at in terms of other opportunities for meeting water demand? Conservation principles, agricultural alternatives, how many of these can we put in place to really think about managing these systems for all these future scenarios and impacts? It speaks to a need for a comprehensive planning tool. It visualizes the entire set of sustainability factors for all of our river basin management, including the surface and groundwater interactions, including planning for finite groundwater supply, and including managing for those inflows. So the watershed sustainability approach really needs to be a goal for SERIDAS. We need to think of the ability of the entire watershed to recover from some of the slow burn, like the droughts and swift heavy rainfall impacts. And we need to think about something that gets us into a position of overall holistic water management. And that is it. Thank you.
Thank you.
Thank you very much, Stephanie. That was quite fascinating. We had one question actually here. It said recent years. I thought it was only 1 year when flows didn't reach the Gulf. Is that a misconception? Or?
So it was that 1 year was heavily broadcast in the media, and that's where that picture was from. We have had past years where it's been very, very, very low flows.
Okay. Thank you. I'd encourage people to ask questions. We've gotten a lot of interesting statements so far, but very few kind of clear questions. We'll save the good ones, or a selection of them, for the very end. But that one was one that I thought you could answer immediately. Thank you very much. So next, we've covered two very comprehensive thematic areas, and now we'll turn to two of these river basins that you've been hearing so much about. First of all, Lars Rebe will discuss the Nile River Basin.
Thank you very much. So I will show my presentation. I think the aim is to talk 10 minutes, so that should be the goal of this presentation. Thank you very much. I'm talking here on behalf of our author team, consisting of Mohammed Khalifa and Safra Thomas and myself. So I have the honor to represent our group here in this short talk on the Nile River Basin, which was, of course, one of the SERIDAS study areas. And the Nile River Basin will be discussed here in three subchapters, and this is the Nile River today, the Nile River tomorrow, and then sustainability pathway. However, the last point, I think, is it cannot be covered in very much detail. Perhaps some ideas here that will be shared. Now, the Nile River Basin, as it is today, is actually the Nile River Basin of a past, a very lively past, as you all know, the cradle of civilization, not the cradle perhaps, but of course a very important one. And this was actually due to climate change around 5,000 to 6,000 years ago, when at that time the African humid period stopped. People moved towards the Nile because it was a safe source of water, and there they met and they merged and they created new civilizations. And this is a very interesting part of our human history, actually, and you see here some references to that. Today we know the Nile Basin more as a basin of ongoing transboundary conflict, and here's a picture from the construction site of the Grand Ethiopian Renaissance Dam, and this is now perhaps the symbol for this conflict, but it's definitely not the only topic of this conflict. So let us look a little bit into this very interesting river basin consisting of 11 countries, having an area of more than 3 million square kilometers. So that is huge, of course, covering around 10% of the African continent. It is, as we assume, as we know, the longest river in the world. Not the biggest in area, though, that's the Amazon. And the riparian countries have currently a population of this is from 2011, so we are now above 500 million. So that is a lot. It's more than the European Union altogether, you know? and far more than, for example, the United States. So that's the size, that's the dimension of this basin that we're talking about. And I think Gerald North mentioned the ITCZ, the Intertropical Convergence Zone, and as it moves towards the north, it brings rains to this basin, especially to the central part, during the months of June, July, August, and even September. So that is the main rainy season in the Ethiopian highland. You can see it here. This is the dark blue spot, especially highlighted here in July, August, which is actually the only non-arid spot. Again, if you looked at the maps that George Watts showed, the aridity is basically covering the whole northern part of Africa, except this one area, which is the Ethiopian highland. And this is at the same time the main source of all the runoff in the Nile Basin. If you measure it at the border between Sudan and Egypt, it contributes to 86% of the inflow to Egypt comes from this rather tiny, compared to the whole basin, rather tiny area of the Ethiopian highland. And that is then characterizing the seasonal pattern of the flow, which you can see here. The red is the total flow at the border of Sudan and Egypt, and then the contribution of the White Nile coming from the southern part, the area around Lake Victoria mainly, and around that. And then the Blue Nile, which is also blue in this curve here. You can also, well, if you have time, you can look at the exact numbers of contributions. But this is the high seasonality, and this immediately asks for somehow storage of water, as we need water in especially the growing season, but actually throughout the year, in order to secure our different demands. And that led to the construction of different dams. I think Jurgen Schmandt already, he mentioned these early constructions of dams in the Nile Basin, and the High Aswan Dam is a very famous one, built already in the 1960s. And so that is an engineered river since almost 100 years, and that is why it's a very interesting case study. Now, how is the water used? Of course, as in most arid regions, the large part is used for agriculture, and here you see also the distribution between the countries. You see always Egypt being the #1 water user. Egypt is using most of the water, as it is almost completely depending on the Nile. 100 million people live there, using it for agriculture, but also industrial and municipal uses. As you sum it up, it's more than 16 billion cubic meters. So it's also significant, and much more than many other countries use altogether. And then you see the other countries, and you often see here in these figures that we talk about Egypt, we talk about Sudan and Ethiopia as the main water users. Now, in some countries, almost 100% is used in agriculture, and others in the more humid regions, less than that. Again, here, the #1 or the three most important water users are Egypt, Sudan, and Ethiopia. But it's also a source of course, food security, the other big topic. So you see here the harvested area, the total production. Egypt by far has the highest production, even though it is not occupying the highest area. This is because they rely on irrigation, very intensive irrigation, and you see here the yield in Egypt is far higher than in the other countries. So that is also to be considered if we talk about productivity, especially about water productivity. Then we see huge differences in the countries. And last but not least, energy. So sorry, these are just numbers, and I just want to highlight here the difference in access to electricity. It's 100% in Egypt, and again very low in many other countries. Also, Egypt is the highest energy consumer. It also has the highest peak demand. However, in terms of hydropower potential, it is rather weak, and you see, well, Congo, I don't refer to it because it only has 3% of its territory in the Nile Basin. But then Ethiopia, you see here, with 162 gigawatt of potential hydropower. This is huge, and so far a small share is used only. Well, with the Grand Ethiopian Renaissance Dam, this will change for sure. So you cannot talk about the Nile without talking about the treaties and cooperation. Again, this is not the main topic today, but this figure tries to summarize it, and only one important element that I want to highlight is the 1959 agreement. This was an agreement, really, it was promoted by the British and really between just Egypt and Sudan. And even then, of course, other countries used water, needed water, but in the decades after that, it became more and more clear that actually the Nile is a basin for all the riparian countries, and the riparian countries, they announced growing demands. And so this was then, let's say, considered in establishing a basin-wide cooperation framework, not a basin organization yet, but let's say an initiative. And this is now more than 20 years ago, actually attempts to create a cooperative framework among all riparians failed, so that there is a cooperative framework agreement, but not signed by all members. And at the moment, again, we are in a situation of low level of cooperation, actually. So this is a big demand, and it asks the question, okay, where are we heading? So the question is, how are we moving forward? And if we look at that as the second important point I would like to cover today, the night of tomorrow, we are basically, first of all, looking at the population development. And again, a lot of numbers, a lot of information here, but I think the shape of these different curves speak for itself. And now there are two scenarios: on the left, low fertility projection; on the right, high fertility projection. Probably we will land somewhere in between, but if you consider now that all the riparian countries have a population of above 500 million, then even with a low fertility, by 2060 we will reach more than 1 billion, and that is already a big number, but it could reach up to almost 1.4 billion. So, and you see here the number, the top countries here are actually Congo and Ethiopia. Now, Congo, as I said, is not that important for the Nile issues, but Ethiopia for sure is. And then you have other countries. Egypt is also still increasing a lot. You can see it here. And then, of course, Sudan. And that is, let's say, this is the driver, actually, population growth, and then it will convert into new projects, new irrigation projects, which are shown here, mainly in Ethiopia and Sudan. Of course, in the more humid south, you will not see so many, at least not big, very big irrigation projects. And then we have here the hydropower projects also planned to happen in Ethiopia mainly. So this will lead to a certain conflict, and let's say the symbol for this is now the construction of this nice infrastructure that you see here. And I think you can imagine the dimension of it just by looking at the photo. It will create a reservoir of 64 billion cubic meters. It will have a capacity. That means it can produce 6,000 megawatts. So that is the total capacity of all the turbines together, and that is let's say 6 gigawatts. That's much larger than most of the nuclear power plants. And so that is the dimension of it. And again, you can look at a timeline here, and it was announced officially in 2011, but it was not announced after any way of let's say prior negotiation, prior talks. It was just announced, we will build the dam, and that of course led to big questions and also big discussions. And so far there is not a final agreement, even though the reservoir is being filled right now. And the recent talks took place less than 4 weeks ago, also with not a final conclusive agreement. So it's something you can follow in the press. I think a very interesting discussion, very relevant, and as I said, not only relevant for the member countries, but also for the whole Nile Basin, because it is at the end an issue of a basin-wide issue. I have to hurry up a bit, so this is why I'm skipping some of the slides. Environmental problems. We could discuss it in more detail. Also, the climate change future here. This figure is from a publication last year from Koppel and colleagues, and which is basically referring to what George Ward said. It's in some places of the world, and in the Ethiopian highland is part of it, probably precipitation will grow. So you could say, okay, everything is safe, but at the same time, evapotranspiration will also grow, and this is more or less compensating the positive effect of rainfall. Plus, we will have growing demands, obviously, with the growing population, and you see already here, even today, there is a gap, and this is these two bars. One is for the normal years and dry years. So if you have a dry year, you have less water available, but you have even higher demands, and this is including, and this is now referring also to Stephanie Glenn's presentation, the environmental demands. This is why we today already have unmet demands, and that is actually the problem. At the moment, we are basically buying water security at the cost of the environment. So environmental demands are not considered. The Nile is discharging to the Mediterranean. Discharge is much less. Also, Stephanie Glenn mentioned the problems related to that. But of course, it is much less than would be considered environmentally sound or ecologically sound. And so we will expect a huge gap between water availability and demand. That is for sure. And we could discuss that in more detail, but let me use the last 3 slides on the sustainability pathway. Again, here, just a summary on what we think could be important. An enabling environment for transboundary cooperation. After that, what I presented, I think this is obvious. Second, we have to, of course, find ways to optimize the use, more efficient use, but also recycling, reuse, and also looking at intensification of agriculture, but not at the cost of having more water use. If you look at the rainwater, the total rainwater of the Nile Basin is around 20 times of the available flow of surface water. So we are talking here about a huge water resource, and that needs to be perhaps not tapped, but it should be considered. And last but not least, what I suggest and what I think is very important is that we have to utilize the potential of the data, the so-called data revolution and of science cooperation. So there's a huge opportunity in using open science, open source data, and other opportunities. And we should look at the role of universities in a stricter sense in that whole development scenario. And here I would like to refer to a recent project we executed on behalf of Nile Basin Initiative, creating an adapted ETA product that is based on the WAPO product of FAO and is adjusted. So that could be an example of how we are advancing data for development in that region, and it can be used in many ways to have an idea of water balance, of water accounts, to understand how much different agricultural systems are abstracting water, but also for drought analysis and drought assessment, etc. The other point I want to mention is also as the role of higher education and research institutions. As an example, we created this Nile Research Partnership. You see the members of that partnership, and the initial members, I would say we are looking for more members. And so the idea here is to create a network of expertise that consists of partners from within the basin, but also international partners with certain expertise. And this network should support the knowledge creation, but also the knowledge exchange. And for example, we are initiating the establishment of transboundary education. So having the idea that people who from the different riparian countries studying in also other countries, being exposed to other cultures and neighboring, let's say, neighboring countries, education systems and so on, that they are very good brokers for peace in the future and cooperation. So this is something that we have to do, understanding universities in a new way as playing a very important role and also taking part in development issues, actually. So that would be my plea to all the other members of our consortium, but also those who are out there and listening to join in this initiative to create and share knowledge. So thank you very much. And if you are interested in more things, here are my contacts, and of course also the contacts of Mohammed, Khalifa, and Sefra. Thomas will be shared. Thank you.
All right, thank you very much, Lars. It's huge and very complicated basin. I'd like to take the opportunity for another shameless plug for Water International. Is that in year 2016, we had a special issue on the Grand Ethiopian Renaissance Dam. We also had a webinar on it, I believe, so, and that should be on the website. So if you're interested in following up, not quite so up to date as what we just heard, but I think some of the background from the legal standpoints and engineering standpoints, some ideas as to the science policy linkages as well. I'd very much recommend that. Okay, now finally, last, and whoa, looks exciting here. The Euphrates Tigris River Basin with Aysegül. I hope I got it close to right. Please.
you could just bring that into presenter mode, that would be great. Yes. Perfect.
To continue. So I will be talking as the last presenter, part of the SERIDAS project on our good old Euphrates Tigris River Basin. I will talk about a selected challenges because we identified during the project various challenges, as you noticed. Jurgen was talking about, Jerry was talking about, and also the other colleagues. I will just highlight some of them and then move to the politics of the river, because this river basin actually brought to our project another complexity of saying that I was always repeating to Jurgen and George Ward that in order to talk about sustainability, there is actually sustainability requires stability and cooperation and peace. And so that's why I will probably talk more about how the water politics evolved in the region. But it's the two rivers, and they make interestingly a single river basin, but it's up to debate if it is two basins or single basin. But there are some geographical characteristics that they originate very close to each other in the highlands of Turkey, and then they are contributed by, again, considerable amount of water from Iraq and Iran. And it's the Euphrates and Tigris. They originate in the 3,000 at least high mountains areas, so it's like a humid or semi-arid region. But immediately after that, they flow thousands of kilometers in mostly in arid region, and they merge again naturally in Shatl Arab about 200 kilometers before they drain into the Persian Gulf. So twin rivers, as we call it, and they have a and they are heavily engineered since 1970s in modern era, and that's why it's part of this project. And the water issue, the rivers become competitive as the states, namely Turkey, Syria, and Iraq, started their large-scale water and land-based development projects in the late 1960s, and in an uncoordinated and unilateral and competitive way. So since then we heard about the rivalry and competition between the riparians, and those dams, the engineered dams, brought like in all other places all over the world, benefits and also negative impacts in the region. And this is I will leave to the discussion, but they brought a change in the system, definitely environmentally, but they brought a great change in the socioeconomic status of the region. And one significant factor, challenge, and also response had to be found in this factor is the irrigation. Most of the water in all three countries, including Iran as the fourth riparian, is devoted to irrigation, because the countries, after their independence, after they consolidated their states, they emphasized irrigation-based development or water-based development, agriculture development, which can trigger industrial development later on. So the green areas are the irrigated areas, but data on irrigable areas, data on irrigated areas, and water requirements are all contradictory. But we know that more than 300 million hectares of land is irrigated in Iraq, Turkey, and Syria. And it's a great challenge because irrigation brought benefits, but along with great structural and institutional problems, including technical problems. So there is the equity problems between the farmers and the state, but also efficiency problems about the methods of irrigation. And of course, the huge problem of salinization. Years of irrigation since the antique period brought a lot of salinization and water locking in the region. So it's a big challenge, really. Gerald North talked about, and he also highlighted the fact that Tigris Euphrates is one of the river basins, which will be impacted very negatively in terms of losing surface runoff, but definitely groundwater resources as well, in not very distant future, in near future. And the scientists are expecting, and they have proofs for that in IPCC, that Euphrates will lose about its 1/3 of, or 1/4 of its water, while Tigris will lose like 1/3 of its 1/4 of its water. So the snow melt will change. Those rivers are generated by snows in Turkey, Iraq, and Iran in the mountains, and there will be less snow, and it's already started, and the snow melting will come earlier, and this will have a great impact in the way the peoples use water for irrigation, energy, and for domestic and industrial use. And the less water will mean more stress on ecosystems. It is already there, and we already had this severe and continuous droughts in the region, and such events can really threaten the even political stability in the region as one factor, not the major factor. So we are discussing this as relates to the Syrian conflict. Coming to the transboundary water governance, I tried to highlight this at the beginning. This is the region where there are the water politics at the various levels is a great interest, and at transboundary level is also great interest. And there had been crises in the past because of building the dams. When Turkey and Syria built the dams and finished the dams and started to fill the dams, the first crisis, luckily it was a diplomatic crisis, but it was one of the symbols of so-called water wars, because at that time Saddam used this as a pretext to threaten Assad regime, and he sent his troops to the Syrian border. But water was not the only reason. Ba'athist regimes were already in political rivalry, but 75 crisis has been regarded as an alarming crisis in the region, and the headlines of the newspapers started to produce in 1990 as well, when Turkey built the largest dam in its water development scheme, saying that the water wars are coming. So water wars did not come, luckily, between the states, but the tension, the confrontation continued. Whereas, as I studied for several years, it's a different region, and whereas there was a confrontation and conflict at the political level, not at the physical level, the riparians also try to construct ways of mechanisms for dialogue. And there's this institution called Joint Technical Committee, which we find it as researchers very valuable, because it's an interstate entity, and it shows that the riparians are inclined for diplomatic solution, and it is operational since the early 1980s, on and off. And it's not very permanent, and it is called time to time. When relations get better, Joint Technical Committee also gets a better mandate. But from the beginning, it couldn't reach its ambitions of defining the basin and reaching a final allocation agreement. So it's an ongoing effort, but it's the only institution alive there. And also, along with this rivalry, the riparian states agreed on some water allocation agreements, actually binding treaties, that Turkey agreed to give Syria 500 cubic meters per second of Euphrates, which is actually in normal years half of the Euphrates flow. And it's an interim agreement, it's a temporary one. It is sealed in the agreement that the final agreement will come where trilateral countries, the three countries, will finalize. But in this interim agreement, and still going on, Turkey gives Syria every second 500 cubic meters of water. And we can discuss about, if we have time, why Turkey did this, because it's an upstream country and it's an atypical move, but it was a diplomatic move, and it is working since then. And also Syria and Iraq agreed on a protocol which shares the river, again Euphrates. They didn't touch Tigris. So both agreements are on Euphrates, which makes them more problematic because it's a huge single basin, and when you put pressure on Euphrates, it makes more complexity. And Syria and Iraq agreed to share the river on cubic meters, where Iraq got the largest share, Syria left with 42%. It was under political pressure. We can discuss this later. So it happened in the 1980s and early 1990. But then we had a period, interesting period, where there was a window of opportunity for cooperation in the early 2000s. And we have seen new protocols on water. We have seen presidents, prime ministers meeting under the high-level strategic cooperation councils, where water became another element of cooperation, along with other socioeconomic development issues or security issues. So it was between 2000 and 2011. 2011 is the start of the Syrian upheaval. And so it's not for me, it's still not a lost decade, because it left with some protocols which are still on the shelves, on the agenda of some nation states. Like Turkey already signed these protocols. It waits for the ratification of Syria and Iraq, but they met at the ministerial level, and they discussed about quite different than the sharing agreements of the 1980s, how to use water, how to use it more efficiently, how to modernize irrigation systems, how to deal with droughts, which are getting more frequent. So it was different understanding than the 1970s and 80s, not only sharing the existing amount, but how to manage the existing amount. And between Turkey and Syria, also other interesting protocols established on the Tigris, on the Orontes, which were very controversial in the Syrian political scene. And Turkey-Syria even agreed to build a joint dam on the Orontes, which is a neighbor river to Tigris and Euphrates. This is a great symbol or great political movement from the Turkish perspective, because Syria never before recognized this border and never recognized this river as a transboundary. So that was a decade, really, that was a great rapprochement. But this is, as you know, as you analyze, as you follow the news, that the Syrian upheaval erupted in 2011, and Turkey-Syrian relations severed, and also the Syrian-Iraqi relations were not very good. So there's the biggest obstacle right now, that there are political instabilities and shifting power imbalances, and there is this bilateral political relations deteriorated between any pair of the riparians. But there is an ongoing track between Turkey and Iraq. So we give a lot of importance to this track, because we have to hold something to keep the cooperation atmosphere on the agenda. So what happened after that? It's not only that the relations between the states severed due to the crisis in Iraq and Syria, due to the invasion in Iraq or the start of the civil war afterwards in Syria, but also the water issue became more complex, and because the non-state illegal actors appeared in the region after the invasion of Iraq, and also they moved to Syria, namely the Islamic State, and they started to use water, controlled water infrastructure, these so-called engineered rivers, the engineered structures, the major dams, first in Iraq, then in Syria, systematically and for a number of years. So this was the worst thing happened in the region in modern era. This was something which was terrorized, but it practically happened, that non-state actors can control water resources and can punish the downstream populations or the states with their actions. So this phenomenon, although Islamic State subsequently lost control of the dams, and it's not a big issue right now, but the region is still hosting a variety of terrorist organizations, and that's why I will complete my presentation by emphasizing that this phenomenon, which happened in the second half, between 2014 and 2018, should instruct the riparian states that they should establish regional security arrangements to preserve and protect their water resources and water infrastructure. And this brings us to my first argument, that there are great challenges in the engineered rivers, like climate change, like population growth, like reservoir sedimentation or groundwater depletion, environmental flow depletion. But here in this region, another big challenge is how to establish peace, how to establish stability, and how to protect water resources during conflict, because the conflict is going on in Syria, and the states should find a way how to control their protect their water resources against these illegal actors. And actually, international law in its many areas, like international humanitarian law, international water law, and human rights law, provide provide customs and also rules, binding rules, which also instruct states like Turkey, Syria, and Iraq how to protect their water resources, how to cooperate for this in the coming future. So hopefully this is a transitional period. Hopefully everything will be restored. Hopefully Syrian civil war will be over. So when it is over, I still make some brainstorming, and I still try to make some prospects about what to do with transboundary resources. And I believe when the peace restores fully in the region, Joint Technical Committee should be revitalized. This is the only institution which brought together riparians, though not successful because of their rigid positions, but it can become operational. And it's also interesting to go back to the treaties or the memorandum of understandings which are signed in the first decade of the 2000s, because they provide variety of cooperation areas rather than sharing agreements, but how to manage together these problematic resources. And I also rely on the ongoing track between Turkey and Iraq, because even though at the highest political level there could be some problems between Turkey and Iraq time to time because of economic relations and because of some joint interests, Turkish-Iraqi water relations are still repairing itself. There are ministerial level talks, there are academic level talks. So I think this track should be strengthened while waiting for Syria. And even Iran should be invited to this track, and it's the only way to go for cooperation and hopefully sustainable development in the region. Thank you very much.
Thank you, Aysegül. That's kind of a profound presentation. That's a very critical part of the world, and those rivers have been a part of our news directly or indirectly for quite some time, for far too long. We can hope, somewhat like India and Pakistan with the Indus, that they'll find ways continue and develop in a more optimistic and positive ways you mentioned at the end. Okay, now we're about 10 minutes over time, but we do have a few questions. I wonder if you are able to stay and respond to them. I think I'm the one who is most at risk of falling asleep. It's about 20 minutes before tomorrow here. But I don't have to answer any questions either. Let me just try to pass on some of them. We have one here from Jose Albiac, a very simple one. I think it was in the context of Stephanie's, which is very simple. What about land subsidence?
Huge. Thank you, Jose. It's a good point. Subsidence is a big issue when it comes to groundwater and the groundwater over-pumping issue in particular. And there is some context to that in the chapter in the book, but I would sum it up with, when you start looking at groundwater and groundwater management, one of the biggest things that you have to really do is have an accurate groundwater availability model that speaks to subsidence and what happens with pumping and subsidence in your area and in your river basin.
Okay, thank you. Here's another one from Stephen Niemeyer, who apparently took a class from Jurgen Schmandt in 1991, 1992, sometime in the last millennium. And you quoted Gerald North, of all people, as saying a decrease of 25% in precipitation resulted in a 75% decrease in runoff. Does the world still work that way? Are those figures still accurate?
Yeah. Am I unmuted now?
Yes, you are.
I'm not sure about those numbers. I don't remember that particular ratio.
That's
So
a long time. It's 30 years, right?
I don't think I can do that.
Okay, fair enough.
Question is. Jurgen, do you have any comment on that?
Okay. That was Let's see here. We have several questions from Manoa Muchanga in Zambia, mostly wanting to know more, especially about the Nile. But let's pick one here. For the GERD, you mentioned negative downstream effects. What are some of the projected or expected negative effects downstream? I think that's for Lars.
Yeah, this is the core of the debate, and obviously the one direct effect is that this large surface that is water surface that is created also is associated with a high evapotranspiration, or in that case basically evaporation from that stored reservoir. There is water that is lost to the atmosphere, so to say. Water is never lost. It's always entering one or the other cycle, but it is not available for downstream uses. And the other big impact will be that since the water flow in the downstream, and that is, let's say, or water is stored, and then also it can be used for other purposes. So it is more, let's say, throughout the year, it is available much easier for irrigation projects in Sudan. So I think it will facilitate the construction of irrigation projects in Sudan, which is a positive impact for Sudan, first of all. But of course, it will eventually lead to reduced flows to Egypt. The biggest impact, and this is now where we could talk about many others, also the environmental consequences and so on, but the biggest impact is expected to happen in the years of filling the reservoir, because we are talking here of a magnitude or a volume that is higher than the total annual flow of the Blue Nile. So in theory, if you fill it in 1 year, you would have zero flow for a year of that. Of course, that will not happen. But even if you spread it, and that the longer you spread it, the less attractive it is for Ethiopia, because they can start with the electricity production later. So Ethiopians want to fill it fast, Egyptians want to fill it slow, and now the negotiations are mainly about that. The first years, the filling period, and that is definitely going to have some negative impacts for downstream Sudan and Egypt. I think I stop here, and there are many papers. I can share papers, also co-authored by some of our team members, but many other papers written about it. I can share some of the links.
And again, I plug our own item from 2016 that there were at least 2 papers in there discussing different modeling approaches to just this issue of how to do an optimal filling.
Yeah.
So
I could make excuse me, Jim.
Yeah.
I was going to refer to Lars' presentation and the satellite picture that I showed in my presentation. I showed the annual average of precipitation, but if you go to the website that's on that same slide, you'll find each month. And so that's a very educational thing to do. You can follow the months, and you can see the movement that he referred to of the ITCZ in Africa coming up in summertime, northern hemisphere summertime, and that's when all the water is dumped there at the roots of the Nile River, and then it recedes away. So it's just a very educational thing to have a look at that website, and you'll find the monthly rain. And what happens to the seasonal cycle? You can't always. Most of the things they put on in the IPCC reports are sort of broad pictures, but seasonal cycle is very important in all of these rivers. And the tendency to get heavy rain in summer depends on how these patterns move as you go through the seasons. So that's all I just wanted to.
That's very helpful. Actually, I don't see too many more questions, but there's one that came up by Nidhi Nagabatia, who has left, so can't hear the answer, but it might be worth discussing anyway. And it was, I think it's a very interesting talk, Stephanie. The impact of dryness and drought conditions is leading to reports of transboundary conflicts in the basin and expanding, but that's not the most interesting observation. It's just expanding. I'm new to this. Expanding the stakeholder discussions in water decision making remain a recipe for conflict. Now we've had 3 discussions of these kind of transboundary rivers implicitly in the Colorado, but also we have the Nile and the Euphrates Tigris. I just wonder if you have a response. Is it possible to have too many people at the table?
Well, I would say most people familiar with stakeholder discussions say that's always the problem, right?
Yeah.
But it's also the only solution. I mean, you know, until you can actually get in there and have some of those hard discussions, you're not going to have any sharing or planning for these water resources. And in terms of the drought, I would suggest, I don't know if John Nielsen Gammon, who is Texas's state climatologist, he and about 10 other researchers came out with a paper in June, I think, of this year, fantastic paper on megadroughts and what climate change is looking like for megadroughts and the very common reoccurrence of megadroughts. So, you know, if we can't plan for droughts as a stakeholder group, how can we possibly plan for some of these megadroughts? So it really speaks to the importance of everyone coming to the table and working together to make some of these decisions.
We found, in general, that the role of the stakeholders defined as irrigation districts, individual farmers, cities, environmental groups, was not consistently sufficiently represented in the water management systems of the rivers. And our argument is we have to find better ways of cooperation and move away from the top down to a more participatory management system.
Yeah.
Okay. Any response to that from either Aysegül or Lars about stakeholders?
Yeah, I certainly agree, and I admire sometimes to Rio Grande because they have this system, at least since the agreement with Mexico, to involve the federal states or the even more local stakeholders. This is what we are longing for in the Euphrates Tigris Basin. And when the window of opportunity was opened in the early 2000s, there was this issue between the states to discuss about how they manage their water for irrigation, for energy, and for cities. And they were exchanging some experiences about how they deal with their farmers. But still, the farmers were very far away from this discussion. And but the states were inclined to discuss their experience about like the irrigation management reforms and so forth. But we are quite away from this. And Nile has a more rich experience in terms of involving in this hugely populated and large area stakeholders. And I believe stakeholders involvement brings diversity and also better management and use of the systems under stress.
Okay, Lars?
Yeah, I think it is definitely the crucial point, the participation. We have to distinguish, of course, different levels. The local level is a completely different story than region or sub-basin level. And then if it comes to the transboundary level, stakeholder participation, of course, is a very delicate issue that is related to diplomacy at the end. And here, I would say the beginning is always a minimum level of trust. So that would be the prerequisite for any kind of coordination and cooperation. And at the end, there are good examples of cooperation, stakeholder participation, also within the Nile countries, but at the Nile basin as such, I think it is still in the very early steps, and where we can see how it emerges.
Yeah, thank you. It's difficult, but impossible to do without it, basically, in all cases.
Mm-hmm.
Okay, well, I think that's actually all the main questions I could find from our audience, which is kind of surprising given the richness of this presentation, but I think they were good questions. And it's also 8 minutes to midnight. So I would like to thank everyone. This really was a great webinar. And for those who are still with us, which is somewhere there, we have about 64 attendees still. I would call your attention to the 9th of December, when there will be another of these. This is a major project, and this isn't the whole thing. There will be presentations on, thematic presentations will be on river basin management and irrigation, and on water transfers, and then the two river basins, is it 2 or 3? I think we have to resolve that. But we have the Colorado River, the Murray-Darling, and the Yellow River. And in the Yellow River, you will see me again, but I will not be the moderator. I will be the presenter. So on that note, again, I turn it over to Scott to close this out. Thank you, everyone.
Thank you so much. And again, I would like to thank the whole panel. A special thanks to our moderator, Jim Nickham, editor-in-chief of Water International. Thanks for staying up late with us here today. And thank you all to the panel, Jurgen Schmidt, Professor Emeritus at the University of Texas, Stephanie Glynn, Program Director of Hydrology and Watersheds at the Houston Advanced Research Center, Aysegül Kibaroglu, sorry about that, Chair of the Department of Political Science of International Relations at MEF University, Gerald North, thank you for connecting with us finally. University Distinguished Professor Emeritus of Atmospheric Sciences, Texas A&M, and Lars Vrieb, Professor at T.H. Cone, University of Applied Sciences. So some of the panel and the IWRA are all on Twitter, so please go ahead and give us a look up and follow us if you are interested. If any of these presentations left you wanting to interested more, feel free to check out our LinkedIn page and continue the discussion there. As a reminder, we will have the PowerPoints as well as the recording of this session up on our website, www.iwra.com. You can find information about the organization, information about the work we're doing, and good links to all the membership benefits that you'll get, including Water International. I hope everyone here in the audience found the insights provided by our panel today during this really special event to be very helpful and gave you the material and ideas to work with in your coming days. And I can tell you that it certainly generated a lot of work and creativity amongst us, and even with myself. So I'd like to thank everyone again and remind everyone that the webinar was brought to you by the International Water Resources Association. We're an almost 50-year-old nonprofit, non-governmental educational organization. We focus on bridging disciplines and geographies and connecting professionals, students, individuals, corporations, institutions, everyone who's concerned with sustainable use of the world's water resources. So if you're interested in knowing more about the association or becoming a member, please go to www.iwra.org. So thank you. On behalf of the whole IWRA office, thank you for viewing the webinar, tuning in today. So thank you, everybody.
Thanks, Scott. Thanks, everyone. Bye.
Good job.
Thank you. See you. Thank you very much.
Yes.
Thanks.
Okay.